Wow. Wow. Okay. There's a lot of people here. Holy shit. Okay. This is exciting. There's a lot of interest in this stuff. That makes me happy. Hi, everybody. It is now unofficially 1 o'clock, so I'm just going to get started. How's everybody doing today? Woo! Yeah, machine learning, right? Yeah. That's the cool stuff these days. Just put that out as your main thing on Tinder. That's what I do. Anyway. Okay, cool. So I'm Siraj. I do this on my YouTube channel, Sirajology, Sirajology. I make a bunch of machine learning videos. So yeah, today I'm going to talk about how to build a neural network from scratch in Python. And by from scratch, I mean like we're building on top of an operating system and an interpreter and years and years of code that everybody else has written. But everything in life is really just a bunch of dependencies. If you do a lot of machine learning, you just start to look at everything in terms of abstractions. It's like so when you see me, what do you see? Just say the first thing that pops into your mind.
Beard.
Beard, okay, beard. What is something that you see when you see a beard, like inside of a beard?
What?
So when you see a beard, what's another word that comes to your mind?
Mature.
Mature, okay. So like when you say beard and mature, I just think of like two nodes and they're like linked together through semantic similarity. They come from the same set of abstractions, and so beard is kind of like mixture of it's composed of hair, and hair is composed of molecules, and it's just everything is just a series of abstractions. The point of all that is that this is what we're building today. It's a series of abstractions, a neural network. And what it's going to do is it's going to take some input. It's just going to be an array of ones and zeros, and it's going to output ones and zeros. So we have a pre-built data set, and it's just going to predict the output given the input. That's all it's going to do. Okay, so let's just get started. And there are a bunch of really cool things we can do, but for this example, we're just going to keep it simple. All right, so let's see how I'm going to do this. I'm going to carry this, and I'm going to type with one hand. That's how this is going to work. Okay. So the first thing we're going to do is import our dependencies. So we're going to import NumPy, okay, and we're going to call it NP. That's the only dependency we're going to use. I really love NumPy. You can do a bunch of scientific computing with NumPy, a lot of data science. Pretty much every library in machine learning besides like Caffe uses NumPy as a dependency. That's in Python. Okay, so first things first, we want to create a sigmoid function. So when we think of a neural network, I should bring up an image of this thing. Sorry if there's like something bad on here. Okay, here we go. Oh no, there's no internet. Okay, Dev Bootcamp. Someone shout out the password.
I geek all week.
I geek all week. Okay. That is a suitable password. Okay. Google.
You have a mic on your shirt.
Yeah, but that's to record it for later. I know. I'm like, why do I need two of these? Okay, so neural network. We'll just bring that up. And then, okay. Yeah, that's a good example. This is what we're building, okay? So these circles are nodes. And we're going to build these nodes. And before we start out, we want to create the function, the sigmoid function. And it's going to be an actual function, like a Python function. Sorry, a method. Okay? And what's happening is our data goes from our input layer to our output layer. And those connections that you're seeing between those circles are weights. And we're going to update those weights over time. So into those input nodes, we're going to put our ones and zeros, a series of ones and zeros. And in the output function, in the output nodes, we're going to see the output ones and zeros. But at every circle, at every node, there's going to be this sigmoid function, okay? And the sigmoid function looks like this, to give you a visual. The sigmoid function that we're going to be creating right now looks like this. It's just a simple function that turns a number into a probability. That's all it's going to do. It's going to take a number and turn it into a probability. So let's build that. So we're going to call it nonlinearity, which is another word for sigmoid. Nonlin. Okay, and then the two arguments are going to be x and then we're going to say derivative equals false. I'll talk about that in a second, why we're even mentioning the derivative here. Okay, and we're going to say, we're going to have an if statement here, and we're going to say if the derivative is true, so that's the opposite case. If it's not false, then we're going to, oh, I forgot the semicolon thing, or the colon. If derivative equals true, then we're going to return x times 1 minus, and this is the function, this is the actual equation. 1 minus x. There we go. Make sure I have all my parentheses there. Okay. Oh, sorry. So that's, okay, so if the derivative equals true, then we're going to return x times 1 minus x. But then, if it's not, go ahead. Yeah.
Question, is it, would x be multiplying the entire 1 minus x term, or is it just,
Oh, good call. Yes, you caught it. Nice job. What's your name?
Brandon?
Brandon. Nice job. Okay.
Another question?
Yeah.
Shouldn't false and true be capitalized?
Yes. I'm loving this. You guys are smart. Okay, here we go. Need to catch up with you guys. Okay, derivative equals true. All right. So now for our base return statement. So this is the, so if the derivative is false, this is what's going to fire instead. I'm going to talk about why the derivative in a second. No. np.exp. All right. Okay. Okay, so if we pass in true, the derivative of the sigmoid is going to be calculated. If we pass in false, it's not going to be. Okay, that's what this is basically saying. And when do we want the derivative? When we calculate our error, when we do backpropagation. That's when backpropagation just means when we train our network, when we make it better and better over time. Okay, and backpropagation is a method to do that, which we're going to get to. So that's our function. That's a sigmoid. That's going to happen. That's going to run in every single neuron. Every single neuron. Number's going to hit those things, they're going to hit the sigmoid, and the sigmoid is going to turn them into probabilities and pass that data on, feed forward, from the beginning forward to the output. Okay. So let's create our input data. This is just hard coding some input data. So it's going to be an array. It's going to be a NumPy array. So it's going to be a matrix, actually, because we can add dimensions to this. So 0, 0, 1. Okay, that's our first row. And then I'm just going to put the mic down for a second. Here we go. Okay, let's see if I got that. Yes, please correct me. Where is that? Oh, right here, right? Top first line. Okay, let's see. There's need to be one more of these, right? And then, sorry?
Prematurely close your parentheses.
Oh, thanks. Okay, let's see. Oh, yeah, there it is. Cool. And then make sure it's like, we'll just keep it here for now. We'll fix it later when we compile. Okay. So that's our x, and then let's do our y. Sorry, that's the 7. Y equals NumPy.array. Okay, so each of these is associated. Each of these outputs is associated with one of these. Okay, so for 0001, the output is 0. For 0111, or so for 011, the output is 1. So let me just format this. Always an annoying part of Python, but it just makes us better in the long run. Let's be real. Okay. Okay. There's one more, right? That one. And then one more up here. Boom. Okay. Okay, so, and let's comment that so we know. Input data, and...
They asked in the back if you can like zoom in at all or...
Oh, okay, yeah. No worries.
I'm gonna see if I can turn the volume up.
Okay.
Maybe, looks like it's max. Just the microphone.
Testing. Okay. I can also just speak louder. Okay, I can do that. I was kind of mumbling because like this stuff is intense, but it's all good. It's Saturday, everybody. Okay. So now we have our input data and our output data. Let's seed. Let's seed this thing. So seeding is good for debugging. It means every time, because we're going to generate random numbers in a second. So seeding is good for us to start at the same point every time. So it's good for debugging because we're going to get reproducible results later on. Okay, so seed. We're going to seed it at 1. So that's the base number that we're going to generate numbers from, whatever our random function is. It's going to apply its functionality to it starting at 1. Okay. So we have our input data, we have our output data, we seeded it, and now we've created our sigmoid function, we've imported it. So now it's time to create our weights, well, as I like to call them, more brain-like synapses, the connections between each of the nodes in our neural network. So let's create our synapses. Okay. So synapse 0, there's going to be 2 of them, synapse 0 and synapse 1. Okay, so we're going to apply this function to our synapses. Okay, I'm going to talk about it in a second. This is our random function. Okay, so this is a 3x4 matrix of weights. That's what we're creating right here. It's a 3x4 matrix of weights. And then the 1 is our bias. That's just for, a bias is for, we can set it to whatever we want, but just for this, and it's one of those things where you can tune it depending on what your data is and what you're trying to do. For this simple example, I just put a 1 as a bias because like you generally always want some kind of bias when you're building a neural network. It doesn't really matter, but we're just going to put it there. Okay, so that's our first set of synapses, our synapse matrix, I should say. And then we're going to create one more. And it's going to do the same thing, so I can just copy this. Except for this synapse, I want it to be a 4x1 matrix of weights. So I'll make it a little bigger. Okay, so that's 4 nodes and then one for 1 output. Okay. All right. Okay, we've got our synapses. Now we can just start to train our network on this input and output data. So let's do it. Training time. Okay. So for training, we're going to, when we train our network, we are continuously inputting that data, and we're updating the weights over time through backpropagation. It's updating all the weights every time. The weights are getting better and better, and the paths between the neurons, are there. It's kind of like you're sculpting. Every time you're sculpting it, it's getting closer and closer to what you want to, the statue that you're trying to create. That's what training is doing. So that's why it's going to be a loop. It's going to be a for loop. So let's make our for loop. So we're going to train this it doesn't matter what the number is, but the bigger the better generally. We're just going to do 60,000. We're going to train it for 60,000 training steps. Okay. Okay, so now we want to create our layers. So these are our layers. So the layers that we saw in our neural network are here. The first layer is the input, the second layer is the hidden layer, and the third layer is the output. So when we say, so we use layers as an abstraction. So we're not actually coding these individual neurons or nodes ourselves like a data structure. Like we're not making a class for a neuron here. We're just thinking of it this way because that's the way the probabilities are. That's the way the probabilities are being calculated. That's where the data is moving. We're just creating 3 layers. Okay, so we'll just name each of those layers. Those are the 3 variables that we're using. L1, L0, L1, and L2. That's what we're going to call it. Okay, so it starts off with X. So that's our input layer. We're putting our input data into L1. That's our first layer, and then L2 or L1. So this is where we apply that nonlinearity function. This is where we apply the sigmoid. Yeah.
Is that a 10 or an L0?
That is an L0, but I did write a 10. You're right. Thank you. Okay. Okay. And so what is this? The dot np dot dot. That is matrix multiplication. We're multiplying the synapse matrix by layer 1. And we're applying the result. Yeah?
Shouldn't it be for J and X rank?
Oh, thank you. Okay. All right, so that's our second layer. And then our last layer, the output layer. We're going to call it L2. We're going to apply the same function that we created up here. The nonlinearity is this one up here. Remember this? Okay. So nonlinearity np dot dot. And synapse 1, our second synapse matrix. So for the last layer, we take the previous layer and the next synapse, and we perform matrix multiplication there, and then we input that into our nonlinearity, our sigmoid function, and it outputs the probability. Okay, and the probability, by the way, the ending probability is our prediction. Like how likely is this output to be this inputs? How likely is this output to be correct? How likely is this output to be correct? Okay, so we got our layers, and now this is the good stuff. This is the golden stuff, the backpropagation. This is basically the machine learning right here. Okay, so we're gonna write down the backpropagation. What it's doing is it's trying to reduce our error every time we're iterating through this loop. It's going to try to reduce the error that the prediction is bad. And the lower the error is, the more likely the prediction is to be correct every time. So we'll write our error. We're going to call it L2 error because it's going to come out of the last layer. And we're just going to arbitrarily put some starting number here. Hold on. I think we'll put that there.
Question.
Yes.
Is layer 0, is it the X matrix that we set up for layer 0?
Yes, that is the input matrix we set up, right up here.
There should be lowercase x then.
Oh, good call. Nice.
Do you need a colon or 30?
Say that again?
Colon.
A colon? Oh, up here. Yes. Or did I put that in? No, you're right. Okay. I lost my place. Where were we? Okay. We're going to arbitrarily put 12 here for the L2 error. And then, okay, so we want to print this error every time. So for our own log, we're going to print it so we know like how well it's training. Okay, so we're going to say for J, and at every 10,000th step. So it's going to print 6 times during training. So we're only going to print it every 10,000 steps. So this is going to print out our error. We're going to use the absolute value function of numpy to make sure it's a positive number. And we're going to get the mean of that and then print it as a string. So that's considered the chain rule. But it's basically just printing our error every time.
Why do
Okay.
you subtract 12? From L2 there?
That is actually an L2. No. No, that is L2. Hey, why did I write that down? Oh, because.
Or you're just taking the difference?
We're taking the difference, and then we're applying the chain rule to it. Yeah. Thanks for pointing that out. Okay, so it's L2. Okay. So now we're going to calculate our deltas. So a delta is just the difference, the difference in the quantity every time that we're going to calculate as we move data through the layers, as we apply the sigmoid function to all of them. All right. So we're going to calculate two deltas, one for L2 and then one for L1. Okay. So L2 delta is going to be, we're going to take the error every time. We're going to multiply it by the nonlinearity. And then this is going to be L2, and then we're going to set the derivative equal to true. That's our first delta. Now we're going to calculate the error for layer 1, and we're going to apply that delta, and we're going to matrix multiply that delta by the first synapse's transpose. The transpose is we flip the matrix. And then we're going to take L1's delta, which is going to be the first error times that nonlinearity function that we had. And the derivative is going to be true again. Okay. So now that we have our deltas, we can update our weights. This is the actual updating part. We're going to take our deltas and we're going to use those deltas, that quantity, that variance, to update our weights. That's the result of our applying our sigmoid function to all of our numbers, all of our input data. We can use that to update our weights every time. So both of our synapses, those are our weights. Synapses, weights, same thing. So we're going to update synapse 1 by taking the first layer's transpose and multiplying it by the L2 delta. And this is just like, we're not going to apply a learning rate term or anything like that right now. That's like if we wanted to do other things. So that's our first synapse. And then we're going to do the same thing for the first layer, and then we're going to use its transpose, and we're going to use our L1 delta as our argument here. That's it. That's the. Let me write that down. So that's how we update our weights. I'm just going to call it synapses. Let's stick with that. Boom, boom. And then calculate deltas. Synapses. That's it. Now we can print out the output every time from our last layer. So we're just going to say print output after training. And this is after our training is over, and that's going to be in our last layer, or L2. Okay. I'll keep that here for a second. There's no way this is going to compile. We'll see. You know the feeling, right? It's like there's no way this can compile. Let's just go. Okay. All right, I'm going to compile this. Oh, that's small. Okay, here we go. Okay. So I called it test.py. Oh my god, it compiled. Oh my god. Okay, so serious time. We did it. Okay, so it's going to print the error 6 times, and you can see the error is decreasing every time. See, it starts off as 0.49, and it goes to this, and it goes down every time. It's getting better and better at predicting. And the output is going to be the associated row for the input, whatever we're predicting every time. So this use case is kind of like, it's a little boring, let's admit it. I mean, we're just putting in ones and zeros, and it's outputting a 0. You can use these things to predict the next number in a series. You can use it to predict stock prices. If you make it recurrent. There are different types of neural networks. This is just a feed-forward neural network. Data goes in one way and then comes out the other every time. So to sum up what just happened, okay, let's sum this up. We imported NumPy. That was our dependency. That's how we're going to do everything. And then we created our Sigmoid function. The Sigmoid function turns all of our input data into probabilities. All of our integers and all of our numbers into probabilities. Then we create our input data, 001, 10, 011, 1001, 111. And then the associated output data. Each of these goes with one of these. They're pairs. And then we seed our script, because we're going to generate our synapses are going to be generated randomly as a matrix, a 3x4 matrix and a 4x1 matrix. But for debugging, if we want to reproduce these results later, like if we were to write a test and say, is this going to output the same prediction? It's good to have seeding, because if we didn't have that, it wouldn't be reproducible. Then we create our synapses, two matrices, and then we start our training. 60,000 time steps. We have 3 layers. Starts off with the input data, goes into the first layer. We apply our sigmoid function twice to the next layers. So, yeah. And then backpropagation. That's when we calculate our deltas so that we can update our synapses. And we use those sigmoid functions to create our deltas and then update our synapses. And finally, we print our output, which is going to be this right here. So you can see that it's 0, 0, and 0.99, 0.99, 0, 0. It's not actually 0 and 1. They're probabilities. It's as close as it's going to get to 0 and 1. But that's pretty good. Look, those are pretty close numbers to 0 and 1. It's kind of like, you know how Facebook had that the caption generator for images. You input an image, and it's like, well, there's a 67% chance this is a, rubber ducky or something, but it's actually like a man or something. It's pretty bad right now. All this stuff is, yeah.
What was L1 error?
The L1 error.
Yeah.
Where did I write the L1 error? I didn't write it, did I? Oh, I did write it. It's right here. Oh, you're asking what it or where it is?
Yeah.
Okay, where it is? Yep. I did. L1 error. Yeah, this is the basic stuff behind when we talk to our phones, when we do anything on the internet. This is the building block of everything now. Even though it really sucks, I had an iPhone, but I switched to an Android because talking to Siri really pissed me off, because oh my god, she never got what I was saying. So I switched to Google Now, and this thing also doesn't get what I'm saying. So the answer is clearly better algorithms, more data, more computing power. But we'll get there. It's gonna be awesome. You just have it in our ear at all times. You know how Apple has the wireless one? Just put it in your ear. That's gonna be cool, because it's gonna be less weird to talk to your machine and be like, Hey, am I doing okay on this date right now? Okay. Does anybody have any questions? Any other questions? Yes.
So your inputs to this were the three integers, right? And each input was a set of three integers.
Yes.
Like a sequence. If you wanted to like read the sequence, what would be like a moving window of
If you wanted to print a sequence,
you want to like predict the next number in a sequence.
oh, predict the next number in a sequence. That's a great question. So this could not do that because this is a feed-forward neural network. For that, we would need a recurrent neural network. So whenever we have anything that predicts the next word in a sequence, so for natural language processing, whenever we're generating text, maybe for a chatbot, or we're even in music generation, when you want to predict the next set of notes in a series, that's a recurrent neural network. This is a feed-forward neural network. So recurrent neural networks are really cool, though. That recurrent neural networks do just what you just said. That they're in a sequence because the data flows back. So the output data goes right back into the input. It just keeps going. It recurs. It's recursive. And then there's convolutional neural networks, which are a whole different ballgame. Just check these out. These are crazy. These are used for object recognition, object detection, and image recognition. And so then you have all these layers with things like pooling, max pooling, min pooling. You can just build up from here. This is just the basic building block of feed-forward neural network. Yeah. So I have 30 more minutes, guys. I think I just finished this a little early, but I want to keep going. Do you guys want to see me build another neural network in TensorFlow?
Yes.
Yeah, right? That's the shit. Okay, let's do that. I'll keep that here for now. Okay, let's do this. Okay. Okay, so we're gonna do another neural. We're gonna build another neural network with TensorFlow and NumPy. Okay, and so what this neural network is going to do is it's going to learn the line of best fit. It's going to learn the line of best fit. Okay, so when you have a bunch of points, you could plot those points, and you want to learn the line of best fit so you can predict the next point in that sequence of points, right? Remember we did this in like 7th grade, 8th grade? Learn the line of best fit, like y equals mx plus b stuff, that kind of thing, but we're going to learn it from our input data. Okay. So we're going to import both of our libraries. The first one is TensorFlow. We're going to call it TF for short. TensorFlow, by the way, Google's machine learning library. It's pretty.
As TF.
Thank you. It's really hot right now. Everybody's using it. All the cool kids are. Import NumPy SNP. That's it. Those are our two dependencies. That's all we're going to use.
Do you get some water? I get to
Yeah, some water would be nice. Appreciate it. All right. Okay, so we're going to start off by creating our input data. So say input data. And we're going to generate 100 phony data points. All right, and we're going to plot those, and then we're going to predict the line of best fit. So our X data and our Y data. We're going to generate a random number between 2 and 100. That's our range for X values. And now for our Y values, we're going to do something similar. Sorry, it's... All right, thanks. Appreciate it. It's going to be a pretty horizontal leaning line. It's not going to be very tall. Okay, so that's our input data. It's going to be 100 phony data points. We'll just say 100 phony data points, and then now we're going to make our model. Okay, so we're going to use a TF variable for our model. So in TensorFlow, there's the variable object. And the variable object lets you store tensors. And you can use these. And so in TensorFlow, let me back up for a second. So in TensorFlow, the reason it's called TensorFlow is because we have tensors. And tensors are what the framework considers all data. It considers all data a tensor. And a tensor looks like this. It's a three-dimensional matrix. So all input data is considered a tensor in TensorFlow. And all of those tensors flow in our neural network, and they flow out to the output layer. That's why it's called TensorFlow. It's just a bunch of tensors that are flowing through a computation graph that we create. And TF variables are nodes in that computation graph. They're the class that TensorFlow uses to represent these tensors. We can put our tensors in there, basically. So that's going to be our bias, and then we're going to create our synapses. So I'm going to say W for weights for synapses, and I'm going to say a TensorFlow variable. We're going to create another one, And we're going to initialize our synapses. Again, remember how last time we initialized them with random numbers? We're going to do the same thing. We're going to initialize them with random numbers using the random uniform function in TensorFlow. And we're going to have these base numbers that these random numbers are going to be generated from. Okay, and now this is our actual line, the y equals mx plus b, you know, the slope formula. We're just going to do that right here. This is going to be a representation. It's going to be a part of our computation graph. And we're going to use the matrix multiply function of TensorFlow, mul for short, and we're going to use our weights or synapses as an input, as well as our input data, x data. And we're going to add our bias, or B. Okay, so let me write down what this is constructing a linear model. Constructing a linear model. All right.
Or parentheses at the end of W.
Let's see. You might be right, yeah. You're probably right. Wait, hold on. Yes, thank you. Lowercase w, thank you. Wait, what? It's fine. It's fine. Okay, so now we want to perform we're gonna perform gradient descent. Gradient descent is an optimization method that we're gonna use to improve our network over time. That's the actual machine learning part that we're doing here. So gradient descent looks like this. This is a good one. That's a good example of gradient descent. So you can kind of imagine it as kind of like a valley with a ball in it. And we want to make sure that our valley is positioned so that the ball goes right in the middle every time, that perfect center point. And gradient descent is basically moving that curve so that it's in the right position for our ball to be right where we want it. It's kind of smoothing the path, the three-dimensional path that these tensors are going. It's smoothing it so that it's going to be the closer it's going to get to, the more we perform gradient descent, the closer it's going to get to that convergence. Okay, so gradient descent time. Yeah. So we're going to create our loss, which we're going to minimize over time. And we're going to create it by using TensorFlow's reduce mean function. And so we're going to use reduce mean because this stuff is actually a lot easier at the higher levels. I just want to say, like, this is like, there's a lot of math happening here. But just after this, just write down Keras, K-E-R-A-S. Like, check out that library. There's a bunch of, like, it's such a readable framework, and it's great. That's kind of like one of the ways I got started, was like looking at Keras. It's a lot more. It's K-E-R-A-S. As a matter of fact, why don't I just take a little break for a second and just show you that. I'm just going to go off track for a second. Keras. Let me show a cool example. So. we're going to do that in a second. We'll pause. But Keras, remember that. Okay, here we go. So we're going to calculate our mean squared error, which is a formula that's going to calculate our loss for us, which we're going to reduce over time. The training step. We're going to reduce our loss over time. Okay. So we're going to use the square function of TensorFlow, and for our arguments, we're going to say y minus y data, and y data is the variable we calculate up here, and then y is the y equals mx plus b function we wrote right here.
That's mean squared error, right?
This is the mean squared error, yes. Okay, and so now we're going to do gradient descent. And we're going to call it, gradient descent is our optimizer. Okay, so we're going to call it optimizer. And we're going to, TensorFlow has a built-in gradient descent function right here, under train. TensorFlow has trained a gradient descent, and then it's called the gradient descent optimizer. They added that word. Okay. And then it takes an argument, which is 0.5. We're going to put 0.5, which is our learning rate. That's our learning rate. We can make this 0.4 if we wanted to. We can make this 0.5. It's one of those things, kind of like you know, like MNIST. There's a really like famous example in machine learning called the MNI, or there's a really famous data set called MNIST, which is handwritten digits. It's in a lot of like introductory tutorials, and in a lot of MNIST examples, there are basically you want to train a neural net to look at one of these images and then say what is that number. So it's using image recognition and saying, oh, that's a 4 or a 5. And that's used in a lot of like introductory neural net tutorials. But the reason I brought that up is because there are numbers that are used in that source code, like 512. It's like, why did you choose 512 for the size of that image? Someone just chose it once and then we just rolled with it. That's just kind of how it is. So that's kind of how I think of like learning rate. Like in a lot of like introductory neural net examples, we choose 0.5 for the learning rate for gradient descent. I mean, it worked and it produced great results. So okay, here we go. Optimizer. Thank you. Okay, so now the train function. We're going to take our optimizer that we just created as gradient descent, and we're going to minimize our loss. So this function is us moving that value and making sure that ball is in the perfect spot. It converges. That's our training set. But we don't actually run the training yet. In TensorFlow, okay, let me start. So in TensorFlow, we wrap our computation inside of a graph. We wrap it inside of a graph, which I'm going to show you in a second. And we can visualize that as well easily using TensorBoard, which is a really cool tool for visualizing your network as it trains, TensorBoard. So before we create our graph, we want to initialize our variables. This is like a standard step that we do every time. So you know how we created these TF variables up here? They're not actually initialized. I mean, we've assigned them to these variables, but they're not actually initialized inside of the graph session until we manually do so. And this is kind of a little bit of magic, a little overhead in my opinion, but like this is what we do. We say tf.initialize all variables, and it doesn't take any arguments. That's it, and that's going to initialize these variables that we created up here for our graph in a second. Let me make sure I spelled that right. Yep, okay. Okay, so now we'll launch the graph, the TensorFlow graph. Boom, boom, boom. So we'll create our session. We'll create our session as a TensorFlow session, and our graph goes inside of a session. A session is just an event where we compute whatever we're trying to compute. And we'll run our session, and we'll use that init variable as the argument to it. Session.run init. Okay. So now that we've created our session we can begin the fitting process, the training process. So we'll say train, and we'll just say like fit the plane. And so we're going to create our loop. Move down a little bit. Okay, for each step in the range, X range, 0 to 200, colon, we'll run our session, and we're going to use the optimizer we created. We're going to just run training just like that. So in TensorFlow, you define your optimizer beforehand, you create your graph, or you create your session, and then you run it using the variable that you define that optimizer as. So this could be gradient descent if we were trying something different, like generally for like text generation, for generative models, we use Atom. Atom is a newer optimizer. But gradient descent is like good old gradient descent. It's always there. So we're just going to use that. So this is where we're going to print our error every 20th step. We're going to print the step. We're going to print where we are in the session. We want to see the value of both of these variables. Okay. That's it, really. And then it's going to learn the best fit values so the best fit as in what the weights are going to be, and then what this bias is going to be for our model right here. We're going to learn what W and what B should be. Okay, so let's run that. Let's see. Hey, do I have TensorFlow even installed on this? Let's see. Here we go. I knew it. Hold on. Are you kidding me? Okay, let's do Python 3 then. Okay, there we go. Missing parentheses in call to print. Print step 131. Oh, that's right, because it's Python 3. Aha. I'll do it like this, right? Something like boom. Holy sh! It's working. Oh my god. So in line 10, function object is not subscriptable. Subscriptable. Interesting error. Anyone have any ideas?
Instead of square brackets, it's a function, right? So
Parentheses. Yeah, let's try that. Yeah, let's try it out. Anything else? Oh, okay. Okay, I'll wrap it up. Cool. Oh my god, we're so close. We can do this. Hold on. X range. X range is not defined. What are you talking about? Oh, X range isn't in Python 3. You're right. Yeah, so it's range, right?
Yeah.
Yeah. Okay. Cool. Yeah, good call. Boom. Output. Right. Method object is not subscriptable. What are you talking about? Oh, maybe it's like these are parentheses as well. Oh, TensorFlow and Sirajology. Okay. No. Never. Yes. It worked. Okay, cool. So it's learning that the line of best fit is when W is let's see, the step W, so the three values here are the step we're at, so 0, 20, 40, 60, 80, and then W, which is going to be these two values between our 1.09, and then it's going to get closer and closer to 0 for the first column, and then it's going to get closer and closer to, remember up here we had 0.2. It's going to get closer and closer to 0.2 right here. So as you see, it's like 1.1999, and then it's going to learn B. It's going to get closer and closer to 0.3. That's what we put right up here for our white data. Okay, and if I had more time, I would show you guys in TensorBoard, but we don't have time. But definitely check out TensorFlow. That's what I've been using a lot of these days. I'm a big fan. Any last? I'll take one more question. Anything. Go for it.
You said you had a YouTube channel?
I have a YouTube channel. Check it out. It's even more engaging. It's SIRAJOLOGY.
Type it out.
Sorry?
Can you type it out?
Yes. Let me do that. Sirajology. Okay, and let me just give you guys a taste. Shameless as F plug right now. I just released a video yesterday. Oh my god, I had so much caffeine. I was just like, oh my god, I gotta release this. What was the video called? It was called Learn Python for Data Science. For Data Science. Come on, YouTube, before they kick me out of here. We got this, we got this. I just released this 6 hours ago. Oh my god, where's the sound though? Are you serious? Oh my god. But anyway, I guess you can't hear me.
Differences are practically unpredictable, and we've invented the sciences of psychology and sociology to help us study these things. Both are the scientific study of people and all the emotion and relationships and behaviors that they display. Traditionally, psychologists would formulate a hypothesis, and to test it, they would find a subset of people that fit their category, bring them into the lab, then ask them to do some task while recording the results. But with data freely available,
So anyway, and so I talk about code like this and
use the
stuff.
OAuth handler method.
We do a bunch of data science, you learn Python along the way. All right, thank you guys, I appreciate it.